Hello Math 1030 team. This is going to be the second video covering chapters 6.2 and 6.3. Technically the material I'm about to present now will be from chapter 6.3, Payout Annuities. So first definition. A payout annuity is an account that starts with money in it, and money is pulled out of the account on a regular basis, usually monthly. Any remaining money in the account will continue to earn interest. After a fixed amount of time, the annuity will end up empty. So a payout annuity is typically the type of annuity that you'll use when you're already in retirement. During your working phase of your life, you save money using a savings annuity. Once you decide to stop working, you're going to start withdrawing money from your annuity. And this is going to be that payout annuity, where you take money out on a regular basis to live on, usually monthly, and eventually the account will end up with $0. Now the formula for a payout annuity gives first P. P is going to be the balance in the account at the beginning of the annuity. It's going to be equal to W, the amount of your regular withdrawal that you make, times the expression, 1 minus 1 plus your interest rate divided by K, the number of times you compound interest per year, raised to the negative KT, all divided by R over K. Now in comparison, you want to notice that this formula looks very similar to the savings annuity. However, in the payout annuity, your exponent is now negative. And this is how I remember the two different annuities. If you're in a savings annuity, let me scroll back so you can see that. If you're in a savings annuity, you're saving, your account is growing over time, you have a positive exponent. Also notice the other difference is your parentheses expression minus 1. While if you're in a payout annuity, now it's 1 minus, the order has changed, and now you have this negative exponent. Now remember, I'm not going to ask you to memorize this formula. You just need to know when to apply it and how to use it. So let's look at an example. How much money would you receive each month from an annuity that is currently worth $500,000 if you want to make regular withdrawals for the next 30 years where the annuity earns 4.7% interest? So we're asking, how much money would you receive? We're asking you to figure out what is W. So let's start with our annuity formula. P is going to be W times your expression 1 minus 1 plus R over K raised to the KT. Don't forget that negative. Bracket divided by R over K. Now we want to figure out what W is. And so rather than doing this in lots of steps, I'm going to do this in one step like I did in the last video. To solve for W, you first have to multiply the R over K to get it next to the P on the other side. So eventually W is going to equal P times the R over K. And then to get W by itself, you're going to have to divide by this bracketed expression. We'll put it in the denominator. So 1 minus 1 plus R over K raised to the negative KT. Now let's plug all of the values in that we have. So your P, your starting balance, was that $500,000. Times your interest rate written as a decimal, divided by 12, divided by 1 minus 1 plus your interest rate, divided by 12, raised to the negative 12. And again, we're saving this for 30 years that we're in payout. And now I'll grab my calculator. Now again, your calculator may be different than mine, and you may or may not always need to put parentheses, but it's nice to be explicit. I'm going to put parentheses here to show that this is all my numerator. So it's going to be the 500,000 times the interest rate divided by 12, and that's going to be in a pair of parentheses. One parenthesis to close off the interest rate adjustment, another parenthesis to close off the start of my numerator. The second parenthesis is my red one that I drew. Divided by, now your denominator. You need to be explicit about your parentheses. So here I'll have one in the beginning and one in the end to signify my denominator. So parenthesis, 1 minus 1 plus your interest rate divided by 12. Close off your parenthesis for the interest rate portion. Now I have to raise it to the exponent. Now you keep hearing me say this, but my calculator clearly makes this as an exponent. If yours does not, you will probably need to put parentheses there. Now, don't forget the negative. Don't use the minus key on your calculator. Use the negative key. So negative 12 times 30. Now I got to get out of the exponent, so arrow over and put another parenthesis. This parenthesis closes off the bracket that was my denominator. Okay. And I get this to be $2,593. And if I round this to the nearest penny, 19 cents. So this tells you that you can receive $2,500 every month for the next 30 years while you're in retirement. Okay. Let's look at another example. Frank's parents want to create a college fund that pays $1,300 each month for 6 years while their child is in college. They found an annuity that pays 6% compounded monthly. How much needs to be invested in the account at the beginning? How much needs to be there at the beginning of the account? Okay, let's start with our annuity formula. So our payout annuity formula should look like, let's do part A here first. Our payout annuity formula is P equals W times 1 minus 1 plus R over K raised to the negative KT all over R over K. Now, last time I had to solve for W, how much we withdrew each time, but this time they tell us. We're just trying to figure out how much needs to be there in the beginning. And that's what P is. P is your beginning amount. So we don't have to modify our formula at all. We can just use it as it is. So here we go. Our monthly payment or our monthly withdrawals are going to be $1,300 times the 1 minus 1 plus our interest rate as a decimal divided by the number of times you compound per year, raised to the negative exponent of a 12 times t, the amount of time in years, which we know is 6 years, all divided by the 0.06 divided by 12. Now, I'd like to make sure you can put this in your calculator. So take a moment, maybe even pause the video so you can work slowly. Plug this into your calculator and make sure we get the right answer. After you have your answer, unpause it and let's make sure that we agree. Okay, let's see if we agree. Now again, every calculator is different, so yours might be different than mine. If you're unsure, it's always nice to put parentheses as grouping symbols. So I'm going to put a parenthesis here and here just to group my numerator of my fraction. So parenthesis, 1,300, parenthesis, which represents my first bracket here, 1 minus another parenthesis that represents how I'm adjusting my interest rate, 1 plus 0.06 divided by 12, parenthesis. Now I need to do my exponent, which is going to be negative 12 times 6. Now I need to get out of the exponent, so I'll arrow over, and I'll put a first parenthesis that represents my blue bracket, and I'll put another parenthesis that represents my red grouping symbol that I use for my numerator, divided by 0.06 divided by 12. Okay, I get, and I hope you agree with me, $78,441 and, if I round to the nearest penny, 37 cents. This is the amount of money that the annuity needs to start with so that it'll fund payments of $1,300 each month for 6 years. Okay, part B. How much total money will you pull out of the account? So this will be your total withdrawal. So remember, you're pulling out $1,300 a month. You're doing that for 12 months a year, and you're doing that for 6 years. So I get that you withdraw a total of $93,600. That's the amount of money that you withdraw out of your account over the 6 years, which is more than your account started with at the $78,000. So now we get to say, well, how much interest did you accrue? So now this is part C. The interest is going to be, well, the amount of money that you withdrew, the $93,600, minus the $78,441.37. And I get $15,158.63 of interest that we got to benefit from while this annuity is in its payout phase. Okay, let's try one more exercise here. Now, there is one in your homework like this. It's very similar. So as you look at this exercise, think about how this will relate to the problem that you have in your homework. This one says, a retirement account has $290,000. That will be used to start an annuity that earns 4.1% interest compounded monthly. The annuity will make payments monthly in the amount of $1,300. How long will it take until the annuity has a balance of $0? How long will it take to empty the account? Okay, let's start with our annuity formula. So again, this is in the payout phase, so we're receiving money. Your payout annuity formula, P equals, it's your regular monthly withdrawals, 1 minus 1 plus the R over K raised to the negative KT divided by R over K. Now, if we plug all the values that we have in so far, then P, the value of the annuity, will be your $1,300 monthly payments, 1 minus 1 plus R over K raised to the negative K. Ooh, let me put some numbers in here actually. One plus your interest rate, which is as a decimal 0.041 divided by 12 raised to the negative 12t, all divided by the 0.041 divided by 12. Now here's the question I want to ask us, is we want to know when these $1,300 payments will deplete the account balance of $290,000. Okay, so the way I approach this is I set this equal to the 290,000. So this will look like 1,300 1 minus 1 plus 0.041 divided by 12 raised to the negative 12t divided by the interest rate divided by 12. And I want to know, when will this equal the $290,000? Okay, so for this example, I'm going to actually plug in the numbers as I go so we can keep track of how I'm solving for t. Now, I did this something similar in one of the last videos where to solve for t, I had to eventually use logarithms. So we'll end up doing the same thing here. So let's go ahead and solve for t in steps. I'm going to do two things in my first step. I want to get rid of this denominator, the 0.041 divided by 12, so I'm going to multiply that over here. So now this will be gone. And then I'm going to divide by the 1300 to get that over here as well. Now to make this look simpler, I'm going to get some decimal approximations of this, but I'm going to keep my decimal approximation pretty long. So here we go. After those two computations, we should have 1 minus 1 plus the 0.041 divided by 12 raised to the negative 12t. Now on the right-hand side, let's simplify some of this now. This will be your 290,000 times the 0.041 divided by 12. And then we'll divide that by the 1300. And I get I think I might have made a mistake here. Let me double check this. Oh, I put in 0.071. I should have typed in 0.041 right here. Let me try this again. I have the 290,000 times 0.041 divided by 12. And then we'll divide that by the 1300. Okay, this looks right. This is what I had in my notes. So this ends up being 0. I'm going to write this to 5 decimal places so I can avoid rounding errors. 76218. Of course, I could keep more digits. I think this will be sufficient. You definitely don't want to round too soon because this will create a significant rounding error. Now I want to solve this for t. So to solve for t, let's maybe subtract this 1 from both sides. So this would be now negative 1 plus 0.041 divided by 12 raised to the negative 12t equals, and when I subtract 1 from this value, the 0.76218 minus 1, this will be negative 0.23782. Okay. And now I want to get rid of this negative in front, so let's choose to divide this side by negative 1, divide this side by negative 1. So I think that'll give us 1.041 divided by 12 raised to the negative 12t equals 0.23782. Okay, now following our previous work, we have to get this t out of the exponent. So we choose to apply a natural logarithm to both sides so that we can use the property that natural logs, any logarithm, takes exponents and brings it in front of our natural log. So this will now give us negative 12t natural log 1 plus 0.041 divided by 12 equals the natural log of 0.23782. Okay, we're almost done. I want to get t by itself, so let's divide this side and this side both by the negative 12 natural log 1 plus 0.041 divided by 12. Now, if I did this correctly, this should tell us now that t is equal to the natural log point, oh, not 0 there. The natural log of 0.23782 divided by negative 12 natural log 1 plus 0.041 divided by 12 parentheses. And now I'll use our calculator to approximate this. Now again, with your calculator, it could be different than mine, but I'm going to put a pair of grouping symbols here just to make sure my calculator realizes all this is the denominator. Okay, let's see what we get. So I have the natural log 0.23782 divide by, now to start my denominator, let's put our grouping symbol that says this is my denominator. The negative 12 natural log, the 1 plus 0.041 divided by 12. The first parenthesis to end off this one for the natural log, and then another parenthesis to end the grouping symbol for the denominator. Okay, and I get this to be 35.09 years. So what this tells me is it'll take roughly 35 years for my account that started with $290,000 to end to a balance of 0, if we're making regular withdrawals of $1,300 a month. Okay, now this now finishes all the examples I had for chapter 6.2 and 6.3 for savings and payout annuities. And this should be all the examples that you need for your homework. However, if you have any questions, please don't hesitate to reach out to me. I hope this was helpful. I'll see you in the next video.